Hi everyone, my name is Elsa Tang and I'm currently a PhD student at UC San Diego working with Dr. Karen Sandstrom. And previously, before joining UC San Diego, I also work at Asia A with Dr. Naomi Hirano. So my talk today will be separated into two parts. The first part is about my previous work at Asia A on star-forming filaments in Orion Molecular Cloud 1. And these results were already published in APJ, and we also have a short article published in the SMA newsletter. And the second part of my talk will be focused on my current work at UC San Diego, studying the CO to H2 conversion factors in nearby galaxy centers. And our results on NGC 3351 is recently published in APJ, and we are currently extending our analysis to more galaxy centers for cross-comparison. And we're trying to identify critical diagnostics for conversion factor variations. So let me start with introducing my 2020 paper with Naomi on physical conditions and kinematics of the filamentary structure in OMC1. So our motivation is to study the Orion Molecular Cloud 1, which is the most active star-forming region near our solar system. And we know that filamentary structure can be commonly seen in star-forming clouds, and it can appear in different size scales. So for example, the picture on the right shows that is showing the whole Orion Molecular Cloud region. So the orange part here is the molecular cloud gas observed in ammonia, and the blue part is showing the M42 observed in infrared. And the OMC1 region is in the overlapped part of the molecular cloud and M42. So the smaller figure on the left shows the OMC1 region that is also observed in ammonia, but with a higher resolution of 8 arcsecond. And as we can see, since the Orion KL is very active, the emission is very bright here at the Orion KL region. So from these two figures, we can see that the whole Orion Molecular Cloud is already a large filament. But in the OMC1 region, we can also see there are hub filament structures with smaller scales, so that there are filaments radiating from the high density core of Orion KL. And so we observe OMC1 in N2H plus 322 with the SMA and SMT. And this figure here is the Orion Molecular Cloud observed in N2H plus 120 with the NRO 45 meter telescope. And the rectangle here shows our observed region. And as we can see, there are no N2H plus emission at the Orion KL region, which is different from the observations in ammonia or most other molecular lines. And also the critical density of N2H plus is higher. So this is the reason why we use N2H plus, because it is suitable for tracing high density and quiescent molecular gas. And here's our results of combining the SMA and SMT data. So from the moment zero map on the left, we can see that most emissions come from the filamentary structure, which have a typical width of 0.02 to 0.03 parsec. And the cross sign here shows the position of Orion KL. So as we can see, although the Orion KL region has very high density, but since the N2H plus molecule is destroyed in active regions, that's why there's no detection of N2H plus at Orion KL. And the right figure shows the moment one map. So from this map, we can clearly see velocity changes among 3 different regions. And especially there is a sharp boundary separating the northern and the western region. And all these 3 regions converge at the location of Orion KL. So here's the result of an MHD simulation of a global collapsing cloud. And from the result, we can also see there are sharp boundaries of velocity changes that divide the cloud into several regions. And all these regions converge to the high mass core at the center. So comparing with our moment one map, our radial velocity structure is consistent with the one predicted by the simulation of a global collapse scenario. So we can expect that the OMC1 region should also be global collapsing and forming high mass stars at the Orion KL. And for line ratio analysis, we also use the high resolution 1:0 map from ALMA and the EROM 30-meter telescope. So from both the 1:0 and 3:2 moment zero maps, we can both see that there are high intensity cores inside the filaments. And on the right, we generate the 3:2 to 1:0 ratio map, where we can clearly see enhanced line ratios in the eastern part of OMC1. And this probably indicates that the radiation source are from the high mass stars in M42, which is the trapeziums that is located just slightly southeast to the Orion KL. And for regional analysis, we also define 3 different regions based on the moment zero maps. So the first 2 regions belong to the filament regions, which include the core regions with high intensities and the lower intensity regions that surround the cores. And the third region is the non-filament regions, which have much lower intensities in the moment zero. So from the ratio map, we also found that the filament regions generally have a line ratio of around 1, which is lower than the non-filament regions. And this is probably because the temperatures are lower inside the filaments. So to study the physical conditions in different regions, we use the non-LTE radiative transfer code RADEX. And so we construct the N2H plus 3:2 integrated intensity model, and also the 3:2 to 1:0 ratio model. And then we compare with the observations to constrain H2 density, kinetic temperature, and the N2H plus column density. So for example, these models can be represented by a 3-dimensional grid, where the 3 axes represent the physical parameters to be constrained. So here we show the slices of our models. So as you can see, the background in grayscale is showing the modeled 3:2 integrated intensity, and the contours are showing the modeled line ratios. And so by finding the overlapped parts between the corresponding line ratios and intensities from observations, we can determine the possible solutions. And here's our result. So for the filament regions, it's clear that the core regions are having higher column density than the lower intensity region. However, there are several possible combinations of densities and temperatures for these 2 regions. And in general, we can see that the core regions is having higher density than the low intensity region. But for the relation in temperature, it may depend on whether these cores are prestellar or protostellar cores, since because we would probably expect higher temperatures from protostellar cores. But for prestellar cores, their temperature can be similar to the low intensity regions in the filaments. And then if we compare these results with the non-filament regions, we can see that in either case, the non-filament region has higher temperature and lower density than the filament regions. And we think this is because the heating source comes from the massive stars outside the cloud. So the dense gas in the filaments can block the radiation if there are no heating source in the filaments. And this is likely why we see the filament regions are having lower temperatures than the non-filament regions. And to analyze the filamentary structure, we also do filament identification. So the figure on the left shows our results using FilFinder in a 2-dimensional identification. And the red lines are showing the identified major axes of each filament. So we compare our identification with the one using ALMA observations in N2H plus 1 to 0. So in their paper, they use a different algorithm called High5, and their identification is based on the three-dimensional data cube. But since the hyperfine components in N2H plus 3 to 2 is much complicated, we only perform a two-dimensional identification on the moment zero map. And although we are using different algorithms, we can still see that the main structures identified are quite similar. And this is probably because most regions have only one component along the line of sight. So as mentioned before, we can see several clumpy cores inside the filaments. So we also performed core identification using clump find. And we identified 10 cores with a typical core size of about 4 arcsecond. And by assuming the shape of these cores, which we assume as ellipsoids, we calculate the core masses using the volume densities derived from our non-LT analysis. So as we can see, the core masses range from 1 to 10 solar mass, and the masses are all smaller than their virial mass, which is probably because the turbulence in OMC1 is larger than typical low mass cores. And from previous papers, we already know that there is a protostar in core number 5. So this is probably why core number 5 has the highest mass to virial mass ratio, since it should be gravitationally bounded. And also, the southern OMC1 is already a well-known star-forming region known as the Orion Molecular Cluster. So this can also explain why the cores in the southern region are having larger line width. And if we compare with the identified filaments, we will see that all the identified cores are inside 3 massive filaments. So we can see there are 4 cores in the main filament, as shown in blue, and 3 cores in the east filament, shown in yellow, and then 3 more cores in the filament 8 in the southern OMC1 region. And we found that these 3 filaments with core fragmentation all have line density higher than 80 solar mass per parsec. However, there are also some other filaments without cores having line density close to or higher than 80. And it's possible that these filaments can also form cores in the future. And we can also see that all these filaments have line density similar to the critical line density, which means that these filaments may be gravitationally bounded and are all possible sites for star formation. And then we also analyze the velocity fields inside the filaments. So first we analyze along the minor axis of the filament and compare with the filament formation model. So based on this filament formation model, if the gas is accreting toward the filament major axis, then there should be a velocity gradient along the minor axis. So for example, in low mass star forming region, some filaments have already been observed to have clear and systematic velocity gradient. And we want to know if the OMC1 filaments also have the same velocity pattern. But it turns out that we do not see a systematic gradient on the 2 sides of the filament axis. Instead, we only observe some local velocity gradients across the cores, and the direction of these local gradients are not consistent with each other. So we think these local gradients could be correlated to the rotation of these cores. So it's clear that the filaments in OMC1 cannot be explained by this model, and it's possible that the filament formation mechanism here is different from those in typical low mass star forming region. And although we do not observe systematic gradient across the filaments, we do observe some local gradients. that could be due to the rotation of these individual cores. And finally, we analyze along the major axis and compare with the core formation model. So based on the core formation model, if the gas along the filaments is converging toward the core centers, then we should see the density peaks corresponding to the position of vanishing velocity, which would lead to a phase shift between the density and velocity variation. So here we show the intensity and velocity variation along the east filament. And so the red lines show the peak intensity of the spectrum, and the blue line shows the central velocity. So interestingly, we do see a phase shift between some of the peaks, which may be indicating that core formation is ongoing in the east filament. However, in the main filament, it's not clear whether the two variations are related. But since we already know some protostars have been observed in the main filament cores, it's likely that this filament is in a later evolutionary stage, while the east filament may be younger, so that we can still see the velocity pattern of core formation. So to summarize this paper, we combine single dish and interferometer data, which is SMT and SMA, in N2H plus 322, and produce higher resolution image showing filaments with typical width of 0.02 to 0.03 parsec. And our velocity structure shows that the Orion Molecular Cloud region is probably under a global collapse scenario. And then most importantly, we use N2H plus 322 and 120 to constrain the physical parameters. So we find that the Eastern OMC1 is having higher 322 to 120 line ratio. And this is probably because there are external heating from the high mass stars from M42 or M43. And we also find lower line ratios in the filaments, which can be explained by the shielding from external heating due to the high density and low temperature of the filaments. And we also find that line densities of OMC1 filaments are similar to the critical values. Also, the core mass are smaller than the virial mass. So all these is showing that non-thermal motions in OMC1 are larger than in typical low mass star forming regions. And finally, we find signatures of core forming gas motions in the east filament, which may be indicating a younger evolutionary phase of this filament. Okay, so I think it might be good to stop here for some quick questions before I move on